classes, because here now I see like 6 and that 7. I don't know, in his lecture also he was saying there are not many, more than 12 or 13. 21 people registered. Because if you are not coming to class, then you are really not doing justice to GR, because that's going to be horrible problem for you. You in the sense who are not coming. Okay, so we are live. Oh, so it's recording.
Yes.
Can somebody see if we are live on YouTube?
I will check on YouTube.
Yes, it's recorded. Oh, so it's on live on YouTube. By the way, I wasn't expecting that. I wasn't expecting that it will record, but it's fine. So what we are going to do is I'm not writing that bad. Good. So, I mean, it's everybody know gradient divergence and curve, but we'll still do it in the curve space time. So, I love. So let's start with gradient. Oh, one thing that I did not mention is that read the questions very carefully in the tutorial, in the homeworks, as well as when you write the exams. Because I think in the third question or the second question of the homework 3, there is a question, what is the meaning of the solution? 90% of people have not written what is the meaning of that solution. And I think more than 90% people I have commented everywhere, in every people's homework, that what is the meaning of solution. Nobody has mentioned like there's a solution, this is for theta equals pi by 2 we get this, for 0 we get this, happy. What does it mean physically? So I think there was one or two, somebody who did that, I mean at least explained that, I think it was yours if I'm not wrong. It was written that, yeah, what is the meaning, like it was specifically mentioned that what is the meaning of the solution. So it's not like just you are solving some mathematics. Sorry?
In which question was
I think it was the second question or third question, I'm not really sure, but I think most of the people got 1 mark less just because of that. Maybe I think yours and Adi, I think 1 mark
I remember.
in the third homework. No, okay.
I wrote it. Yes.
Oh, you wrote it? No, I don't know.
No, I don't.
So I think it was the second problem or third problem. I don't really.
It's fair, I think, that you need to solve the geodesic equation.
You need to solve the geodesic equation for the two specific cases of I think theta and phi, if I'm not wrong. And then you need to explain what does it mean.
Pi over 2 and the constant phi.
I mean, I don't exactly remember, but okay, something like that. And yeah, there were some people who did it very nicely when the first question was asked, prove that the space is flat. Some people calculated the Riemann curvature tensor of the space even without Riemann curvature tensor being taught in the class. But since it was right answer, I cannot say that it was wrong or I cannot deduct the marks, but don't go ahead, or maybe you copied it from somewhere else. I don't know, but I was really amazed looking at, like, some people really wrote that we can calculate the Riemann curvature tensor of the metric, and that's how we can prove that it is flat metric, but I think Riemann curvature tensor Asaf taught last lecture.
Yes.
But before that, somebody already knew Riemann curvature tensor and calculated it and gave the homework.
Maybe you knew it from math. Someone took
No,
differential.
honestly, we just looked at, like, I didn't do that, but we just looked at lectures afterwards to get, you know,
No, it's
both
fine.
Curvature, so it really.
Yeah, because I
Given
think
that,
Adi asked me a
yeah.
question about homework. I also like how can we prove that it's a flat space time. So I think I gave him two like kind of a solution how we can prove. So first, first means the most plausible solution if you are given the metric in future to calculate whether it is a flat or not. So the first thing that you do is mostly calculate the Riemann curvature tensor. But since you don't know Riemann curvature tensor at the moment, like till the homework that was given, you were supposed to calculate it by checking whether you can get the flat metric by Minkowskian transformations. I think most of the people already have done it. I don't know how did you do that, because to me it feels like some people had very nice copy paste stuff from somewhere. But okay.
Is it possible to prove the two manifolds are isomorphic if you know their Riemann curvature?
Two manifolds.
The two spaces are actually the same space with different coordinates if they have the same Riemann curvature. Because I know if it's zero, then well the space is flat.
The space
but if
is
it's
flat.
non-zero, like that's a more general.
The question is,
it's
different manifolds can have the same Riemann curvature.
tensor. Yeah, that's I'm not really sure whether it will be the case for like it's like 100% case that if the curvature tensor is same, then manifold will be same.
I think it's not.
Like,
It's not.
it-
If you have both flat spaces radial and the flat space is Minkowskian, they both have zero
Mhm. Yeah, so I mean, yeah, that's what I'm saying is like in some cases it may be true, but in all the cases it may not be true. So my answer for now, I mean, I'm not 100% sure, but my answer is like for like what I can say. It's not necessarily that if the two are same, that means it must be both having the same curvature. It may be or may not be. Most probably for both of them it may not, it will not be. So okay, what is gradient? We can talk about homework later. What is gradient?
Sum of partial derivatives.
That is mathematical definition. Come to physics department.
Density of the
Direction of
Direction.
The maximal direction.
Direction to the maximum.
Okay. So it's in a curve manifold, the gradient is a co-vector field. That gradient we also call as a one form. Did you read it somewhere? No. So
No,
that
it's
is
not that.
yeah.
you already, yeah.
Asaf used the one form.
Asaf used the one form name,
You
right?
use term one
Yes.
for.
Okay. So yeah, because I remember if it is not explicitly mentioned, and in exam if it comes like a one form, then people will be like we were not told what one form is. So if something has the 2 or 3 different names, try to remember the name so that if the questions are phrased in different form, like Asaf has tendency to mold the question completely differently, so you know what is asked in the question. Okay. Okay. So the gradient of a covector or one form that points in the direction of a greatest rate of increase, right? So how we, I mean, I'll just write in simple form. Do I need to write it? I will write it. No, I don't.
No tutorial notes, so maybe.
No, I will give this to, I will upload it in Moodle.
Okay.
You don't need to worry about. That's why I prepared this time notes, so I can put it in Moodle. Okay, so I will write it. the gradient fine.
We don't really have direction.
I mean, it's well,
We don't really have a concept of direction.
yeah, it's then. I mean, I wrote this definition from the like physical understanding point of view. Of course, this is not the mathematical definition. So what I'm trying to tell is what gradient is. It tells you where the maximum gradient of a scalar field is. I'm fine. Okay. And how do we represent it? So delta mu phi is d mu phi. Okay. This is the covariant derivative, of course. For a scalar field phi, the gradient I can represent it like this. So where this is the partial derivative.
Yes.
Yes.
Is just the covariant.
It is.
These are directional derivatives, so makes sense.
Yes. So, I mean, you can write it in the form of like if it's a spatial derivative, take x, y, z. Okay. And what will be the kind of, what can you have, give me some example of what is the gradient, like gradient of something. Like you can give the gradient of temperature in this room. By the way, here gradient is quite large, so somebody turn on the air condition. If it is not, is it on?
No.
Turn it on.
No, it's not.
It is on.
It is?
It just comes from the back of the class. So you
Okay. Okay, so example will be temperature of a fluid. Am I right? So let's say I have a scalar T which represents a temperature of a fluid. The gradient will be, if it only depends upon the spatial stuff, means the spatial coordinates, then I can write, by the way, this is same definition. You should all remember by the end of this semester, this is how my x looks like. I already told in the last class, my x and n looks the same, but this is x. So if T is the temperature of a fluid which depends upon only on the spatial indexes, then I can write the gradient of the temperature as dt over dx, where I takes the values 1, 2, 3, right? Oh, this reminds me of a problem in homework. Some people have written, if you are taking the spatial, if you are told to take only the, I forgot exactly how was it, like if you are working in the spherical coordinate of r, theta and phi, so don't use 1, 0, 1, 2, use 1, 2, 3. Did you understand what I mean here? Because some people were calculating Christoffel of r as this. This can be, I mean, I'm not saying this is wrong, but this is difficult to understand, because when 0 appears to me, it feels like okay, now is the time component. So when you are working in the like a 3 dimension only, try to work with the Greek indices, right? These are the Greek indices. And IJKs, no.
No, Greek is when you have time.
Oh, Greek,
And
yeah, you
Latin
have.
when
Oh,
you-
Lat. Okay, so these are the Latin indices.
Yes, Latin.
So alpha, beta, gamma is the Greek indices.
Yes, that's when you have.
IJK, yes. So when you are working in the 3 dimension, try to use 1, 2, 3, like that, because 0 means the time component. Because when I was checking it, I had to really understand, because some people are writing 1, 2, 3 and some people are writing 0, 1, 2. So I don't know whether it's the R component or theta component. Okay. That's it for the gradient divergence. I will have to solve some problems. I will just tell these things.
Actually, a question.
Yes.
Well, the thing you just erased,
Oh.
del mu t, isn't that the same notation as a covariant derivative?
Yes. So this one, you mean this one, right?
Yeah. No, with a del.
Oh no, so it is my bad that I'm writing it this way, but try to remember it this way, because yeah, I know that will create confusion in there, so it's better to remember it this way. Okay. What is divergence?
The flux density.
The flux from an infinitesimal series.
Yes. So it's a flux density. The divergence of a vector field in a curved space-time generalizes the concept of flux density. It measures how a vector field spreads out from a point considering the curvature of a manifold. I think this was there in the, I don't know, electromagnetism course also,
Yes.
right?
Just follow. Yeah.
The first course in electromagnetism also you have the gradient divergence and curve.
The theorem of divergence, closed line, right?
Yes.
The hairy ball theorem.
Sorry?
The hairy ball theorem
Oh,
does
yes.
relate to the divergence. Because we have the
I haven't read that, so I cannot say. No. I mean, I need to look at it. I have not read that theorem, so sorry. Okay, so it measures this is plus if it is written alone. It is T if it is written with something else. So this is something, because you will notice, because this is not plus, this is it. So please try to understand that. How much vector field spreads out from a point considering the curvature. There are some things that, okay. Let's say I have a vector field A mu. I can write del mu A mu A mu is equals to del mu this fine?
Is it new?
Oh, this is
What's the
new. It should be little curly.
Is it the divergence? The new a new? The delta new a new? Because the divergence is the sum of the divergences. I think it should have the same talking about.
Oh. Also here, right? This would be mu, right?
Yes, it should be. I think.
No.
No.
Because that's
No.
just,
No.
yeah.
No.
You're taking divergence.
The
You don't
divergence is at zero. It's
Divergence.
scale up. It's scale up.
No, so
The divergence is the scale up field, but you have here the tensor field. So you must have the same indices. You must do something with contraction. Or we get a 1-1 tensor field and not
I
zero.
don't understand.
Scale up field. I think you must have the same bottom and top indices or else you get a 1-1 tensor. And the divergence is a zero as a scale.
So you mean that here should be new?
This should be mu, yes. You have the same bottom and top indices.
Just a minute. No, it should be mu.
I think so.
No, so I'll check it out. Need to. So what I am trying to do in here is to write the covariant derivative of vector the tensor A nu. So this is the covariant derivative.
Yes, this
Of
is
A.
covariant.
This is covariant derivative.
Yes.
So
It's a zero, this is 1-1 tensor. The divergence
This is-
should be,
this is not 1-1 tensor. This is 1-0 tensor.
no, I know, but when you have the covariant derivative, you get a 1-1 tensor. Because when you have different indices on top and bottom.
Okay. But this I need to verify
So,
myself.
If
I-
you-
so there is
yes,
a problem with
makes
the
sense.
index.
Then there is a problem on the indecent on the right hand side.
If you think
And
about
also-
Maxwell's,
I don't think, like, if it's
Like,
supposed to be a tensor
classical.
and not a scalar, you can just sum up all the things, right? So you actually do need to have mu there. There you have
Yes,
a tensor,
in Euclidean space.
No, I mean,
just,
that's-
a 1-1 tensor. I think
That's I mean
it has to be mu.
that has to that's why I don't understand that.
No, no,
I'm
mu.
trying to understand.
well, if you think about divergence in kind of a more classical sense,
In
then
Euclidean space.
yeah, say in Euclidean space, then in electromagnetism the divergence of B equals 0. That's dou Bx over dou x
Plus to be y over to y plus to be.
Yeah, it's the same in this. So if you generalize it, I don't think there is a reason for it.
Okay, so I will check out before I put this thing on the lambda. Okay, so but one thing, but here I'm not going to prove this thing, but I'm just going to write it. Covariant divergence of a contravariant vector variant vector is V mu is equals to d V mu over d x mu plus gamma mu lambda. Are you happy with this? This you should be. You must be. You have already studied the covariant contravariant vector.
Yeah.
Yeah, at the start.
I am getting some very difficult responses. I don't know.
No, we already saw it.
Okay. So what I will do is to use the symmetry property of the Christoffel Christoffel is also called something else.
Fine connection.
Affine connection. Yes. Good. So it's mu lambda is this is fine because this is just the Christoffel.
Yes, what's the right hand equation? Why is the right hand equality?
Here I use the symmetry property of second and third. We switch this because this will switch the sign and those both will go to 0. This you can prove. These two things, this will, because what I wrote in here is this term multiplied by this term only, if you check.
Why again? Why you do this first? Why the second and third terms cancel?
What about the first?
Wait, this is what I have written, right? G mu rho, okay. DG rho mu.
Okay, we switch the indices because
That's what I'm saying.
Rho and mu has to be the same, so cancel.
Yes.
That's the thing because of the G mu.
Because that's what I have in here, mu.
No, you have here the G mu rho, which is
Yes.
supposed to be right.
Yes.
Which is supposed to be 0 if mu is not equal to rho. So
No,
No,
the
that's
metric
only for
doesn't
flat.
have to be that.
if, okay.
The metric
No,
does
that's
not
the
even
reason
it has to be symmetric.
we switch the indices because we're summing with both of them. Both mu and
Oh.
mu and rho are dummy indices, and we switch with both of them.
This
Same result.
both cancels out, that you can prove. If you are not happy with it, because I did not write it here, so I cannot tell you now, but
It's
this,
only if G is symmetric.
Yes.
Hmm?
I think this is true only if G is symmetric.
Yes.
Do we assume
Only if J
in
is
the course
symmetric
G
it
is
works.
symmetric? Because in the homework,
In
made
the
this
homework,
assumption
they
a
wrote-
few times,
Yes.
and they don't know if we can make it always.
Asaf told
No,
us
so-
that it doesn't have to be.
no, so here I have used, so okay, here I have used the symmetry property. I already told that I can use the symmetry property of the Christoffel,
No, but you use some symmetric property of the G.
the metric itself.
Yes.
The symmetry in the Christoffel indices is also
So-
is true only if the G cancel
J itself is symmetric.
itself is symmetric.
Yes.
Ah, okay.
But it doesn't have to be always.
Yes.
You can
Ah,
have
okay,
cases
so that-
where the J
okay.
is not symmetric.
So the symmetry of this means that you are saying the symmetry of the metric itself.
Yes.
Yes.
Okay.
We assumed a few times in this course. that
If you assume that, so you can-
multiple times, then we have.
Okay.
The G is symmetric. And if not, you will not have the symmetry. Stop the symmetry. You will not have
the less.
Okay,
the-
then-
you will not have
That's factor
the
one
flat.
between-
You don't have the well, yeah, it's not well defined.
Yeah, because I'll come back to Lambati. This is fine. Okay.
If you assume
Only
symmetry.
if G is symmetric.
Yes,
Only
if you
if
assume
it-
symmetry.
Okay. Now I'll use the. This is some algebra that I hope you know. Trace of matrix M inverse M of x is equals to d over dx lambda determinant of matrix. This you have proved it somewhere in maths?
No.
dx in inside m minus 1 is x lambda, right?
This is d over dx lambda.
No, you don't have lambda in here.
So the x is the whole vector.
No, this is a partial derivative. So these are partial derivatives. This is not the whole derivatives. That's how we write partial derivative, right? Ah, okay. This, unfortunately, I cannot prove now. I mean, this is, I don't know, second year algebra, first year algebra. It can be proved. If you want, okay, come to me later, I'll prove. If I mean, first I'll have to prove for myself, because I did not prove it. I hope that you, I mean, I thought that you were already aware of this. Properties.
The logarithm of the determinant.
Yes, and
This is a given.
sorry?
We can take this as a given.
I mean, well, okay, you can consider that it's a given, but it's a truth. This can be proved as well. And okay, there are many things in here where I am skipping some steps in between, which you need to somehow convince yourself. If you are not convinced, try solving by yourself. If you are not convinced, then come to me, I can prove it. But it's better if you solve by yourself first. Okay. So what I can do is to apply that where m is equals to g mu mu. I can write it there somewhere. For m is equals to applying it to m is equals to g rho mu. Then I can write mu lambda equals to 1 over square root of. Then here most of people will have problem. How did you get this? This is not a straightforward thing, so do I have the proof to this? I don't think so. I had it earlier. No, this one I don't think I have. But
Should it be
Did-
minus?
sorry.
Shouldn't there be minus inside the square root? Or just take
No.
No, that's why it's a absolute. That's why absolute value is written there. Use this, and prove this. If you want, you can read the textbook, Steven Weinberg, I think chapter number 4 or 5. I will, when I upload it on Lambda, I'll put where I took my notes from. Okay, and using this, now I will write the covariant divergence of a contravariant vector.
Where did the half go?
It's
The half goes inside the line to make the square root.
yes.
Oh,
And now I'll use this thing to write the covariant divergence of a vector mu, sorry, v mu, covariant divergence of v mu, which will be v. It's visible from here. I hope so. Mu will be 1 upon square root of g d over dx mu over square root g v mu. I think I do have proof to this, but okay. I can write the covariant divergence of a vector we knew this way. Now I will somehow try to convince you that I can write it this way. Let's see if I wrote my solution the right way. If you find something is wrong, you can tell me. So there are these small proofs that you need to make use of in order to get this thing proved. What I can do is I can write this mu as mu plus gamma mu u v mu, right? So v mu. This you are happy with? This is just the contravariant.
Yeah.
Okay. Now what I will write this as v mu plus d. No, I will write it this way: ln of square root g of nu u nu. Oops. V nu. Now you will again have problem. How can I write this as this?
You got it. Yeah.
And they should have absolute value of the data.
Oh yes. So how will I get this from here? I also wrote the proofs to that. For that, let's see if I have this. What I want to do is to write it like this. Okay, that's what I want to prove. Again, I will write the same thing: gamma mu nu lambda g mu lambda mu plus g mu lambda mu minus mu lambda g lambda mu. Okay. Here this can be written like this, but I'm not going to prove that to you now, because I already proved that this is equals to this. Now here it is equals to this. Now again, if I'll prove that there is another term will come out of it, then I'll have to prove another. So there are like 6-7 identities which I need to continuously keep on proving one after the other, which you can
actually have that also. If you just prove these,
Yeah, exactly.
You get,
fine. So this I can also write as d nu ln of square root of g. This is what I have written in here.
Also,
You call it-
isn't it supposed to be lambda instead of mu at the end of gamma mu lambda? Like if you're going,
Yes.
So
it's
you-
gamma.
you're summing over mu, right? So it's not supposed to be at the end of the, like at the equation. The other side.
No, it depends on. It's not summation.
But it's not all.
I didn't get where you are telling me to. So you want this to be lambda?
Yeah, because like if you go from the other side of the board, you get that with the derivative of mu over there. You had gamma mu, and you did it with the derivative of mu. Here you did it with the derivative of mu, which is quite different.
No, but this is a soft selection. So I don't think it should be wrong.
No.
No, it should not be. No, but we are trying to prove it from here, right? So this is equals to, I can write it this way, which is this.
No,
It
this is
should be
fine.
mu
The thing
instead
is,
of mu.
the thing is that at the beginning of the board, you had gamma mu 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 equals to ln square g with the derivative of mu, and there you had it with the derivative of mu instead of lambda. So if you want to get one from the other, kind of like
No, she's right.
goes.
She's right. Because the second and the third elements cancel out, so you're left with the first element, which is derivation according to nu. From the gamma, from the fine connections.
So I don't remember which, so you were talking about this equation, I forgot which equation was it, where
You can look on the board in the fine connections expression you have.
yes,
The second and the third elements cancel out,
this one, yes.
so you are left only with the third,
First, yes,
which is derivation according to nu. In this case, it's lambda from the indices of the gamma of the fine connection.
no, that I understood, but I don't understand. So
So it
here
should
that
be
should
lambda.
be, here it should be lambda.
Yes,
Yeah.
should be lambda.
Okay, but I really need to verify this. I'm not really sure about that. Because I need to check Weinberg. Okay. Okay. It looks like that's what it should be.
Oh, in the last line in the middle, it's ln of absolute value.
This is this one, right? Yeah, here. This is nu, not v. So I'll use it in here. We have v mu yes, plus t mu of oops v mu, which is what I can write there. Oh, I erased it already? No, it's in here. 1 upon square root of g t mu yes square root of g v mu. Is that? Okay. The thing is, these topics are not really well explained because the things are like, it is understood that you all know these things very well. But so in exam, mostly this kind of a question can be asked. Like because if you see, I think in homeworks also there are these kind of questions, prove that this is equals to something else. And in most of the cases, you'll have to prove something which comes out with the square root of g terms. So you need to really be careful about how to prove those things. Okay, so what can be the one of the example of that? I can write, I don't know, do I have that example? Yes. You already proved that example in your homework. There is one example.
The homework is due next week, so
Oh.
divergence of the stress energy tensor. This is proved, right? I don't know.
Oh, we had it in the lecture. We said that it's zero. I don't know.
We didn't prove that.
I don't think there is a proof of that. It's a fundamental law.
You prove this. You use this thing to prove that you get the
we
constant
used it.
Oh, okay.
We didn't
entropy.
prove it.
Ah, okay.
Yeah.
We use it in flat space. But
Yes, that the entropy, no, the isentropy process, the entropy will remain the constant.
Yes.
Yeah, so this is one of the example that the straight divergence of stress energy tensor.
Just
Zero.
wanted to make sure in that transition from the second to last line to the last line,
Yes.
you use well, actually no, not that you do it, but that if you take the derivative of the logarithm of the determinant of the matrix, then that is the inverse matrix times the derivative of the determinant. Like the derivative of the log of x is 1 over x. So if you take it to be a matrix, then it's instead of 1 over x, it's the inverse matrix.
Yes. So G mu nu, the inverse of G mu nu, what will be the inverse of G mu nu?
With after.
No, that's what I was trying to tell. No. I know how to write that. I mean,
Oh, the value is
this.
no, this is not what I meant to ask. I don't know.
It's not equal.
No, this is not what I meant. So you have problem from here to here. No, from here to here.
Actually, yeah.
From this one to this one.
Like if you take the derivative of the logarithm of the determinant of the matrix.
Yes.
Oh,
So
yeah,
it's
okay,
a-
never mind.
it's a
It's not-
determinant.
You already
It's already the
erased it.
determinant.
The line
Yes.
that
Yes.
was written before.
Yes.
It said that the derivative of log of square root of absolute value of g
Yes.
was the inverse of g
G is
times
not
the
a matrix.
derivative.
G is not a
G.
matrix. G is the determinant of the matrix.
This
G.
this is the determinant. I did not write this.
It's the
This
volume
this
without
this small g is the determinant of G mu nu. This is
minus
not the,
determinant.
yeah, minus of determinant. This is not the G mu nu. What I am writing in here, this is the determinant of metric G mu nu, not the metric itself. Oh, I forgot to mention that. If I forgot, then my bad. Okay, so this is one of the example of the divergence. Curl. How do you define curl? How do you define curl?
With the Levitch.
Sorry?
I said with the Levitch.
Okay, what do you mean by curl? That's what I meant. With the Levi-Civita tensor.
How much a vector field rotates around
A particular point, okay. So I have a particular vector, of course. So a curl of vector in a curved space-time extends the notion of a rotation or the circulation of that particular vector field. Do I need to write that? No. So okay, if I have to write the curl in 3 dimension, curl, rotation, or circulation, not circulation, or circulation of a vector. You have that example of sink, water going in it mix. I'm making sense here, right? So when you put on your tap
Oh, right.
and
So
you
you
see in the
can-
sink,
yeah.
you see those circulation. That
Yeah.
you didn't have the fluid dynamics course, okay? Example. Yeah, next semester there is a hydrodynamics and fluid mechanics course that one of my friend is teaching. Hopefully you will. Okay, so example is vorticity of fluid. I don't know if you know the vorticity of the fluid or what is vorticity.
The curl of the
Yeah, exactly. It's a circulation. So how do I write? Sorry. Let's say if I have a vector field A mu. For a vector field A mu, for a vector field A, how will I write the curl? Del cross A of mu or nu 1 upon square root of G mu lambda del mu A lambda. Right? That's how we write a curl of a vector field. And what is the vorticity? Vorticity is simply nothing but the measure of the local rotation of the fluid. That's why I gave you the example of that sink. When you when you start your tap on, you see those curl of the water going inside the pipe, right? And how you write it is the same thing. Why do I need to write it again? But still, I will write it. Omega mu, which is equals to del cross velocity vector P mu 1 upon square root of G epsilon nu lambda del nu V lambda. I am very lost all the time. Okay. So we are done with gradient, divergence and curl. Okay, good. Now what we have is the okay, so what we can do is from the divergence we can prove that the classical Gauss theorem. From this we can prove that if the vector, yes, from this we can prove that this one, if V mu, if vanishes at infinity, why? If I have symbol, why am I writing infinity? Then I can write the integral of d4x square root of g v mu is equals to 0. I think I do have some, right? How do we write first the Gauss theorem in the electrodynamics? Gauss, it's theorem or no? It's divergence theorem. Okay. Gauss divergence, because I try to remember it like divergence and curl, and the curl is called Green's theorem. Green's theorem, right? Okay. It's better to remember the gradient divergence curl rather than somebody's name. That's my preference. I don't know. So let me know if I'm wrong. Del A into dV is equals to happy? This is what is it? What is this? ds? Surface element. It's a small surface element. This is volume element. Okay? And what I want to prove is that in the covariant form I can write this equation as the covariant divergence as for any vector A mu, for A mu I can write del mu